Welcome back. This is week 9 of Graduate Statistics, University of Cincinnati. So we're working with an example to answer this particular question. Is there a difference between the average vocabulary scores of Americans from different self-reported social classes? And our data set has the scores as a response variable and the classes as explanatory variables, which have 4 levels: the lower class, the working class, the middle class, and the upper class. So we're trying to solve this problem. And you already know a tool to solve this problem, which is t-tests. But t-tests would require multiple t-tests to be run between all pairs of means, which would result in multiple comparisons. And we'll see what the problem of that is. But I raised already 2 little words for you: not efficient, not conservative. We'll know exactly why not conservative in a little bit. So what we'll use instead, that it's a more efficient and more conservative method, is to compare means using analysis of variance, which will require a new test statistic called F. So let's see what are the hypotheses that an analysis of variance will test. The null hypothesis is that the mean outcome, here the score in the vocabulary test, is the same across all categories. Here would be mu1 would be lower class, mu2 working class, mu3 would be middle class, mu4 upper class. But if you had 5 variables, k would be 5. If you had 10 variables, k would be 10. But the point is that the null hypothesis is that all of the means are the same, which makes the alternative hypothesis be that at least one pair of means are different from each other. So here we have 4 different means related to the vocabulary score of 4 different social classes. What I'm saying is that the null hypothesis, to be true, requires that the 4 of them are the same, are equal. The alternative hypothesis requires that at least one pair differ from each other. It doesn't require that every mean is different from each other. It just requires that at least one pair of means is different from each other. Yes? Okay, keep that in mind because that's important. Let's dive into the difference between ANOVA and t-test. For t-test, we compute a test statistic that is a ratio of mean difference to the variation in mean difference, the expected sampling variation in mean difference. And really, every test statistic is sort of this signal to noise ratio. The signal is the difference that you see, the correlation that you see, and the noise is the amount of variability that is in there, okay? The ANOVA will also compute a test statistic that's a ratio, but of a different sort. This ratio, which we will call F, the F that we observe in our sample, is the variability that's observed between the groups, how the mean vocabulary score differs between the groups, so the variability between groups will capture that, over the variability within the groups. The variability within the groups in vocabulary score functions as the noise. If the variability within groups is as large as the variability between the groups, then probably nothing is going on, right? So an F observed of 1 tells me that, the amount of variation that happens between people in the same class is pretty much the same as the variability that happened between people that are in different groups, which tells me, maybe class is not really relevant for explaining vocabulary score, right? But if the variability between the groups is much higher than the variation that we see within the groups, then there begins to be a reason to believe that something may be going on, all right? We'll dive into that a bit more in detail in just a little bit. For now, I want you to understand is that both t-tests and ANOVAs will imply that we compute a statistic that is that has on the numerator the signal, the pattern in the data, the difference, right? The difference, however bigger the difference is, the higher the signal. But the importance of that signal magnitude will vary depending on random variation, right? It's the same thing here. Variability between groups is the signal. It's going to be high if there is a lot of difference between groups, and variability within groups will be high if people just differ within the groups. That's the noise, right? So the signal needs to be substantially higher than the noise for us to get high enough T statistics and high enough F statistics for us to say that they're unlikely to happen under the null hypothesis, for them to be at the tail end of the distribution. So large test statistics lead to small p-values in both cases, because large test statistics is telling us that the signal is overpowering the noise, the variation, just by chance. If the p-value is small enough and the convention that is that small enough is less than 0.05, HO, or the null hypothesis, is rejected, and we conclude that the data provide evidence of a difference in the population means. And that's true for both t-tests and ANOVAs and z-tests, and every single test that we're going to do. And that's when I mean that the process is the same every time, and it's the process of data analysis and hypothesis testing that is the focus for me that you understand. Okay? Now, the F statistic, because variability is always a positive quantity. Remember, in statistics, variability is always variation around a mean value. It's always positive because we square it, remember, to make everything positive and average it. Because that's the case, F will always be a positive value. And what we have is a distribution that has only one tail. So larger Fs, large positive Fs, will fall on the tail of the distribution, and we'll have a rejection area that has 0.05 probability, and any F value that falls on this region will lead to the rejection of the null hypothesis. All right, so one more time with feeling, let me get out of the way of these writings here. In order to be able to reject the null hypothesis, we need a small p-value, small meaning by convention less than 0.05, which requires a large test statistic, because a large test statistic is what will take us to the tail of the distribution, to the rejection area, rejection of the null hypothesis area. Obtaining a large F statistic requires that the variability between the groups is higher than the variability within the groups, within each of the samples. Now, how are these pieces of the F ratio calculated? That's what we'll see next. But I'm lying. See how today I'm not good? My memory, let's move on. I digress. So now, before we go on and discover what are the pieces that go into the F ratio, I want to go over the conditions and assumptions of analysis of variance that must be met for us to trust ANOVAs to get our answers. Just like we had it for z-tests and t-tests, we also have conditions to run ANOVAs. The nice thing is that they're pretty much the same. We need independence. Within the groups, the observations must be independent from each other, and between groups as well, when you have a non-pair design, which is what we're exploring here. We need approximate normality, so the distribution should be nearly normal within each of the groups. And just like in t-tests, when you have multiple groups in independent design, what you want is that you have equal variance across the groups. Okay, so Levine's test will come back in this week's assignments as well in order to test this particular assumption. Okay? Again, how do I guarantee independence? Can't really guarantee, but there are signs that suggest that we might be meeting this assumption, which is random sampling. I am sampling randomly from the population, or if I use the convenient sample, I'm sampling from the UC undergraduate students for my research. I need to at least be assigning them randomly to the different groups. So either random sample or random assignment. Each group needs to have a size that's less than the 10% of the population they represent, which is typically true because sample sizes tend to be small. And always important, but again, difficult to be sure about. So we need to bet on if these things are true, then we say we can assume independence. But again, it's difficult to know for certain. And groups must be independent of each other, right? If they're not independent from each other, if the means of the different groups have a special type of correspondence, maybe you're evaluating people prior to treatment or prior to some kind of intervention, a month after, a year after, now you have 3 means again, and they're all coming from the same person, so they have a correspondence. Then what we have in this case is a repeated measures ANOVA, which is just a different kind of ANOVA, but the logic behind it is very close to the logic behind the most simple ANOVA, which is the means coming from independent groups, which is the one that you will need to explore and learn how to do. The others you'll be introduced to, so you understand the logic, but you won't be required to know how to run them. All right? Again, another assumption is that it's approximately normal. You just should check this for each group, and a way to do a quick x-ray of that is box plots. Remember, if the median is really at the mean of the box, it's a good indication that the distribution is pretty symmetric, unless it's uniform. That's why it's good to look at the histograms as well, because the mean could be in the middle of the box also for uniform distributions. So if the distribution is not uniform and you have a symmetric box with the median in the middle, it suggests a pretty symmetric distribution. Because sample sizes are small, it's always good to check with numbers. Check your skewness, check your kurtosis, just like we did for t-tests, okay? And again, histograms are nice when you have large sample sizes. When you have small sample sizes, they barely ever look nice and symmetric. So that's why box plots are kind of useful to double check. Again, estimates of skew and kurtosis, the difference between mean and median, all of these things together will help you determine, is there a substantial deviation here from normal or not. I should mention before we move on to the next piece that there is a form of statistical test that you can run to determine whether the distribution is normal, but it's very common for this test to turn out to tell you that it is normal because of power. So that's why I like to use these multiple pieces. And if most of them are falling into place, then you decide, the deviation is not great enough for me to not run my analysis. Constant variance across groups. Variability should be consistent across the groups. There's a term in statistics that's homoskedasticity. So groups must be homoskedastic. That just means that the variation within the, the variation, the sizes of these distributions should be more or less the same. And if we look, this spread is not very different. This one seems to be a bit greater, but then the tail is also less great. So most likely, Levene test will tell us that we can assume equal variances. So yes, this value of standard deviation should be pretty close together and not varying that much across the groups. And we have Levene's test to actually go in and test the null hypothesis that variance is equal across all of the groups, just like we did for t-test. All right, once assumptions are met, we're ready to go in, dig into the data and analyze it, thinking that our hypothesis test will be performed using an analysis of variance in this case. All right, we'll come back the next video and dive into the analysis proper. See you then.